Good evening, everyone. Today we are going to look at the flight test assignment 4. This will be our last flight test assignment for this semester. Uh, and then there is supposed to be one more, but we don't have time for that. In this assignment, we will be trying to find the neutral point of an aircraft. It is something which you must have learned in 514. So you're just going to do the flight test to find that. So the instructions still remain the same. I think I forgot to add the COVID regulations. I'll update it. The problem, let's go to the problem statement. So we are going to identify the location of the neutral point in a Cessna 172. We'll go through the test procedure, and then from whatever data you have got, you're going to go back and verify whether you have done correctly. So for that, we are going to fly a separate test point, and then we are going to find the static margin and the elevator angle required for that particular flight test point. I mean, we'll discuss all of this one by one right now. So let's go for the problem one. Let's discuss the procedure. So there are going to be 3 CG locations. We are going to use the datum, that's wherever it is right now. Then we are going to add 6 inches to it. And then the third condition is when you subtract 2 inches from it. So this is to make sure that you get 2 points, one on either side of the datum, so you get a nice straight line. The procedure to change the CG is shown below. I'll show you how to do that. So we have to fly a trim condition of 100 knots at 5,000 feet altitude. And after establishing the trim condition, you change the indicated airspeed using only the longitudinal stick input. So that means once you have stabilized and everything is good to go, leave the power where it is, and then try to change the indicated airspeed just using your elevator input. You cannot do anything else. You cannot roll. You cannot try to avoid roll as much as possible. And you have to fly at the speeds. So you'll start at 100 knots. You can slow it down to 90. Then you come back again for 110. Then you can slow it again to 80. Then you can come back for 120. So that way you'll be doing something like this. Okay. And there will be an altitude loss or altitude gain. That's fine. So all we have to do is, in order to maintain, we have to maintain altitude within, I think it's supposed to be 200 feet, not 2,000. I'll look into that. So all you do is just alternate the high speed and the low speed point. And at each point, collect the following data. You will note down the CG condition, and then you're noting down the elevator deflection, the indicated airspeed, weight, altitude, and the true airspeed is something which you can calculate. I don't know whether Explain gives it. I think it does. And then there will be 3.
Scroll up a little bit with the layout.
Oh.
I'm trying to zoom in.
I don't know why it's not zooming in. Oh, there we go. Okay. No problems. And you have to understand that we are flying 3 CG conditions. That means we will have 3 tables of each one for each condition. And inside that each table you'll have at 4 points: 120, 110, 90, and 80, and 100. Sorry. Okay. So we are going to fly and maintain a level flight for 5 seconds, and then we note down the data. So let's go for any questions till now on how to, for the test conditions and data collection. Any questions? Okay, we'll go to data processing. So first step, we'll convert all the indicated airspeed to true airspeed or from the X-plane. And then you convert all the elevator angles to negative elevator angles. It's because of the conventions in X-plane and what we actually use. And then plot the true airspeed versus elevator. And then we prepare the next table where we calculate the Q bar and CL, and then elevator from X-plane. And if you want to use any data, like for example, the wing area and etc., use the Appendix B aircraft aircraft A in appendix B, sorry. And then you will plot CL versus elevator and also calculate the average intercept. So you have 3 tables, right? And that means you will get 3 lines. You have 3 plots, and you will have a linear trend line for each one of them. So you'll have 3 straight lines. Ideally, they should meet at the same point. In this case, it won't because it's a flight test. So take the intercept for all the 3 lines and average it out. That will be your ideal intercept, approximately. So we need that data for what we are going to do in problem 2. So once you have those 3, once you have that graph, then you can also plot the CG versus slope. So each one of these lines has its own slope, and they are for each of the CG conditions. So for this CG, you have to take the CG from the book for cruise condition, and then you have to add or subtract how much ever inches I have given. So I don't know what the exact value will be. So for example, if it says 20% mean aerodynamic chord, then they should give you how much is the MAC, and if you have any issues, let me know. So once you have that, then you'll have literally 3 points. So there are 3 lines from the previous step. That means you have 3 slopes and then 3 CGs. So you get 3 points. And then that should, you can approximate it to a linear trend line. And once you have that, substitute y equal to 0, you should get the neutral point. Do you understand this process? I mean, I know it looks complex, but once you start going through it, it should be easy. Any questions? Okay, so once you have finished this, you would have finished problem 2. Problem 1, sorry. So once for problem 2, you are going to go backwards. So for problem 2, we are going to fly the aircraft at CG plus 12 inches, and you have to find the stick fixed static margin. I hope you guys know the formula for that. And then you also have to calculate the elevator angle required for trim with the CL from flight test. So you fly a condition at 100 knots, 5,000 feet, CG plus 12 condition, and then you will note down the elevator from X-plane, and then using the CL calculated or from the X-plane, you are going to go back. So once you know the CG, you can calculate the slope because you have a linear trend line. So that means if you know CG, you can calculate the slope. Once you know the slope and using the average intercept here and knowing CL, you can calculate the elevator deflection. So that's how you go backwards. Once you look at the data, it should be easier, but let me repeat. Once you know the CG, using the trend line, you can calculate the slope. And once you have the slope, using the average intercept and the CL, you can calculate what the elevator deflection should be. And whatever you're calculating should probably match what you're actually flying with. This is a nice test point where you can actually see how your results can be used. And just answer some of the questions like, does it match the flight test? If it does not match, why? Things like that. Any questions? Okay, I'll leave it at that. And the assignment which we didn't get to do was the fugite mode, which would have been fun because you'd be actually exciting the fugite mode of the aircraft and try to find out the damping, the frequency and the damping factor of that particular mode. But anyway, we don't have time for that. But so any questions, please feel free to email me, and we can figure it out. Thank you.
Thanks, Balaji. Hang on, Balaji. This is probably the last time you'll see Balaji. So tell him thank you for putting these flight things together. Who knows, someday when you're interviewing for a job or at a job and somebody says, does anybody study any flight testing in school? You can say what now? You say yes. And who knows, it might get you a job, right? Or it might impress your boss. Or somebody will buy you a beer. I don't know. Thanks, Balaji. Did everybody get a handout? If you came in late, you didn't get one. Anybody come in that did not get one today? This? Oh, I thought I could get it to stop up there. Anybody else? So this handout is key to the lecture today. What I've done is gone through the book and copied different pages throughout the text that we're going to collect together to do what we're going to do next, which are the perturbed dynamic equations of motion for longitudinal flight. So we're doing dynamics now. And we're going to solve these equations using Laplace transforms, which is what you've been studying in 607 and reviewing. And we've been covering some of the first and second order modes. So the first page on your handout okay, so it is auto-focusing, just wanted to make sure. First page on your handout. Looks like this. So these are the equations from chapter 1, small perturbation equations. We have the x force equation, the y and the z, the roll, pitch, and yaw, and then the three kinematic equations. And these are perturbed about a steady state flight condition, U1, V1, W1, P1, Q1, R1, psi1, theta1, phi1. And then we've already done this before, but we'll just walk through it again. We're going to make some assumptions to specialize these for cruise flight. So we're going to do steady state, straight line flight. I think this marker is dying as well. So just like we've done before for this condition, the angular rates are 0 steady state. That doesn't mean that during the perturbation flight they won't change. And then we're going to say no side slip. So no initial angular rates, no initial side slip. We're going to say no bank angle. To start out, the airplane can bank during the small perturbation, but that's 0, and we're doing stability axis. So W1 is 0. And like I said, this isn't anything new. We've specialized equations using these conditions for cruise. So we go through in these equations and knock out Q1, V1, R1, V1. Do that in the kinematic equations. And we get the equations on your next page. So flip to the next page. And here it shows those conditions here as well. And so here are the equations that you get when you make all those assumptions. And again, we did this in chapter 1. So this is nothing new. We're just walking through what we do. Notice these were not for stability axis, so W1 is knocked out. And eventually we'll say, well, we're going to do this for level flight, so theta 1 is 0. But we can leave that in for now. But notice that Q is theta dot, and that makes it really simple. That's because there's no bank angle. So in the kinematic equations up here, the bank angle terms, that goes to 0. There's no pitch angle. There's no rates here, so it's psi 1 dot. All of those rates are 0. Bank angle is 0 here. So the only thing you're left with is this term right here. So that simplifies those equations quite a bit, just saying no bank angle and no psi 1 dot, no rates. Doesn't mean we couldn't do this for another case, right? We did pull-ups and stuff like that, but it just makes the equations more complicated. All right, so these are ordinary differential equations. We have U dot, V dot, W dot, P dot, R dot, and Q dot. And turns out theta dot is the same thing as Q, so we'll use that. And we just spent several weeks developing the small perturbation forces and moments that go in for these terms here. So that's what I've done is I've collected those for you down here. So this is the matrix for longitudinal forces and moments in terms of these variables here. So notice we have some more dynamics now. We have Q and we have alpha dot, more ordinary differential equation terms, and then the thrust forces and moments. And so we shove those in to the equations up here. I'm going to do this equation here. So follow the process, take good notes, because in the homework, you're going to do the next two. So this is the starting point. In the homework, it says start with these equations. So I'm going to write that one down and plug in for FAX and FTX from this set down here. Actually, I want to put this in brackets here, so there's a minus sign here. All right, so this is this perturbation velocity term from the forces and moments. And then this is the thrust forces and moments. This is the thrust X force times U over U1. And I put this in here because I want to keep the U's together. And then we've got the drag term. And this multiplies to alpha. So again, I'm just copying from those equations that matrix. And all this gets multiplied by Q bar S. For this equation, he drops out this term. He says that CD alpha dot is about 0 and CD is about 0. You don't have to do that. We could process these terms just like we're going to do the rest of the terms. So I think I've got everything here. There's U, there's alpha, alpha dot, Q, and elevator. And all of these are small perturbation variables here, remember. So you'll do the same thing for the lift equation. Sorry, you're doing the lift equation, so it's the third one in the list. It's the mu dot minus u1q equation. Same exact process. You'll stuff this stuff in where you have FAZ and FTZ. And then you're going to do the pitching moment equation, so it's the middle one down in the second set of 3. It's going to look exactly like this. And for this equation, we're going to divide by m. For the z force equation, you're going to divide by m. And for the pitching moment equation, you're going to divide by I, y, y, because you'll have an I, y, y over here times q dot. And the whole point of this is to get the derivative over here all by itself. So let's do that step. So we're going to end up with u dot is equal to minus g theta cosine theta 1 Let me scoot this down a little bit. So minus and notice that I've collected all of the stuff that's just numbers here. U is the small perturbation variable, so put that out here and then put everything else here. And I say it's numbers because like the mass is a number, the flight speed is a number, the dynamic pressure, number, you get the point, right? Area is a number, CDU is a number you look up in the back of the book. CD1, that's just the total drag of your flight. So those are all numbers. This is the dynamic variable. So if we wanted to be precise, we'd be going through here and putting of t, a function of t, on all the dynamic variables. But we're just going to keep track of that in our head because we're smart, right? So what are the dynamic variables? All the small perturbation. U, theta, U, alpha, alpha dot, Q. In fact, maybe we can list them up here. So the variables in all these equations. So the dynamic variables are u, v, and w. And we know that alpha is equal to w over u1, so that's where alpha shows up. And then we got, in fact, beta is v over u1. And then we got p, q, and r, and delta E, delta A, and delta R, but these are the inputs. So those are the pilot inputs. So these are the variables that are in here. And we're going to solve the 6 equations for these 6 unknowns, U, V, W, P, Q, and R. So these are the inputs. Just like F of T, the force on the second order system. And then these are the X's, the position. So these are the state variables. All right, so collect all of the non-dynamic variables here. We're going to do the same thing here. Again, each term we're going to multiply the Q bar S into the term. And then our variable out here is U. And then we got the alpha term here. Alpha is a dynamic variable. I'm going to leave these in it for a minute just to show you how these work. I get everything. I got the Q bar S, got the C bar 2U1, M, CD alpha dot, and this multiplies alpha dot. And you can do the same thing with the CDQ term. C bar, Q bar, S over 2, U1, M, and that multiplies Q. And then I've got this last term here I'm going to squeeze in down here at the bottom. So I guess this is step 1, is take the dynamic equation and substitute in the forces and moments. Step 2 is to divide by M. Everybody caught up? So all we're doing is algebra from this point, yeah.
Are we adding that first term to all these terms?
Adding what term?
G, beta, cosine, beta.
Yeah. This is a minus sign. Let's make that better. Plus a minus this thing. Yeah.
There's supposed to be a U1 with a CD alpha plus CL1 term.
Boo, no. How did I throw that in there? I just got caught up in the under U, or the dividing by U1, didn't I? Thank you. It's there, it's not here, and it's not here. So I was doing unintelligent pattern recognition. All right, so I pointed to this when I said number. Obviously, 2 is a number, number, right? For a given airplane, those are all numbers. And so going forward, we're going to have to Laplace transform this plus the other 2 equations you're doing. Getting tired of writing all of these fractions. So we give them names. Just like we give people names. I have a name, Dr. Steck, and when somebody introduces me, they call me Dr. Steck. They don't say the guy that was born on 1634 Bessie Street in Cape Girardeau, Missouri in 1958, went to school at SEMO and then went to Rolla and then worked in St. Louis. And you're right, you don't say all that stuff. So we're gonna give this a name, and we want to call it something where we can keep track of it. Yeah.
I'm confused. Where did the D1 go for the alpha and C?
I erased them because they shouldn't be there. Oh, crap. Oh, man, I'm not doing well with my U1s. There is a U1 here, and there's a U1 here. So add to my list that I just listed is the person who couldn't keep track of U1s on November 5th, or whatever the day is. So let's go through that again. So we're just dividing by M, and so the U1 should be here, the U1 should be here because I pulled the U's out. Should not be a U1 here because there's no U1 in sight, but there is a U1 here and a U1 here, right? And we got the 2's there, so that's good, and I didn't do a U1 on the delta E term, so we're good there. So circle this thing, and we're going to give it a name. And circle this one, we're going to give it a name. Name this thing. Notice I'm including the minus sign if it's there, so make sure you do that. So circle all of these numbers that multiply the dynamic variable. And this is the effect of U on the X force equation. Which sounds like a branch of the military. So that's the X force equation, and it's the effect of U. So just to keep track, in this book, and a lot of books, he calls it X subscript U. All right, so we call that XU. It's the X force equation. Here, this is the alpha effect. So we're going to call this one X because it's still the same equation. I'm going to put an alpha. And how about this one? This is another U effect, but it's the thrust effect. So we're going to call this XTU. And so immediately you look at that, you go XU, oh yeah, that's the thing that multiplies U in the X force equation. So what should we call this? Yeah, we'll call that X alpha dot. Now, when you look in the book and he's doing this derivation, he doesn't have this term because he knocked it out, but I left it in there so I'll show you when you're doing the Z force equation, you get a Z term there rather than an X term. And then we call this X subscript Q because it's the X force equation times Q. And then we call this X delta E. I'll have to squeeze it in down here. So immediately we've taken this giant mess and we've collected these things under names. So that's step 3, is to define what are called dimensional derivatives, as opposed to non-dimensional derivatives, because these have dimensions. Yeah.
So one was the U dot, 2 was U dot, and 3 is
Step 1 was to plug in the forces and moments. Step 2 was to divide by M. And step 3 is to define these groups of terms. And notice how much easier our equation has gotten now. I lost alpha. There's alpha. And in the book, these are gone, the alpha dot and the q, because he says those are small, but not in the z-force equation. So those dimensional derivatives, in case you ever forget what they are in a nice table in your book as well. And I've copied that in your handout. So they are on page 319. And these are the longitudinal dimensional stability derivatives. And they have units. So they're all collected there for your convenience. So your job is to do this equation, the longitudinal equation here, and this equation here. Same exact process. The nice thing about this whole deal is, here's the equation we just did. Here's the answers for the equations you're going to be doing for homework. So you know what your target is. Make sure you show the process, because guess what I'm going to grade? Not the answers, because the answers are here, but make sure you show the steps. All right, so now we have 3 equations and 3 unknowns. We have u, alpha, which is related to w, and theta, which is related to q. And notice here he's plugged in for q, he's plugged in theta. For q dot, he's plugged in theta double dot. So to get to this point, you are going to use the fact that q is theta double dot and that alpha is w over u1. So we have 3 equations, 3 unknowns. They're dynamic. So we Laplace them, because that's how you solve differential equations in a nice, convenient way. It's not the only way. So I'm going to Laplace this one. You're going to Laplace the next 2. No, sorry. Q is theta dot, Q dot is theta double dot. Yeah. So if you Laplace this, we're going to do it with 0 initial conditions. So I guess this is step 4. Which means we get S times U of S for the derivative. Theta is the variable here. That's dynamic. All the rest of this stuff is just numbers. Yeah. What? Oh, I'm not sharing. So we Laplace. These are real easy. The U's just go to U of X's. And again, these terms are gone. I'm just going through the motions here. You get S alpha of S, Q is theta dot. So that's S theta of S. And delta E is a time function, so it's delta E of X. So you get an algebraic equation. So this is the first equation. And then you're going to get 2 more. So we have 3 algebraic equations. with 3 unknowns. The unknowns are U of S, alpha of S, and theta of S. Yeah. The what? I'm missing it. Here? No, because the S alpha is alpha dot, right? Right, when you Laplace. Yeah, that's the magic, is it turns derivatives into S's. So we stick these 3 equations into a matrix because that's a handy math tool for solving multiple equations and multiple unknowns. And you're going to be doing that with your 2 equations and this equation. And the answers for that are on your handout as well. So after you Laplace, you get this. And then you put it into matrix where the unknowns are U, alpha, and theta. And notice that he's gone through and divided each equation by delta E, because here he has U of S over delta E of S. I think you can figure out why he did that. In 607, you get transfer functions, right? Which are output divided by input. That's what this is. U of S over delta E of S is the input to output transfer function for U. Alpha is the input to output transfer function for alpha related to elevator. So elevator is the input, and U, alpha, and theta are the outputs of the system. So he's just taken each of the equations and divided by delta E. So you get all of the unknowns divided by delta E, so you get those transfer functions. So you have answers to the homework all the way, and we have what we need to solve the dynamic equations, because now we're going to solve the algebra here. It's a matrix equation, and we want to solve for each of the unknowns. So we're going to use Kramer's rule. We'll come back to that for a minute. So we have a 3x3 matrix with 3 unknowns. Does anybody need to write anything down from here? The top equation? Everybody's good? Because I flipped over to that, so I want to make sure you have a chance to get something if you couldn't see it. I'm erasing. Are we good? Are you still writing? You're good? Okay. Yeah, usually I teach this class where I can project on the screen and use the whiteboard at the same time, so you can see both at the same time. So if I get ahead, say something. Okay, so what we have is a matrix like this. And I'm just going to write terms for the A matrix here. Where what's in here are the terms in that previous matrix. And so if we use Kramer's rule, to get the first unknown, and notice if you look at this matrix that we had, that you have on your handout, it's a polynomial in S, right? You see S's different places and everything else is just numbers. So we're going to get polynomials here. And Kramer's rule says you take the matrix itself and you shove in the right-hand side. And then you keep the rest. You take the determinant of that, and then you divide by the A matrix, the whole thing up there. And since all of the stuff in the matrix and the stuff on this is just numbers here, and this is S's, we end up with a polynomial in S here, and a polynomial in S in the denominator. And if you need to convince yourself of that again, go back to that handout and look at what the A matrix is. Yeah, so here's the A matrix, right? It's S, XU is a number, XTU is a number. So all of these symbols are numbers, and you just have S's. So this is written out exactly what I'm just kind of sketching out on the board here. So we go back if you want to catch up here. So all of this stuff, again, is in your book. I've Xeroxed portions of it. Actually, I've Xeroxed all of it for you in your handout. So as soon as you're caught up to what I have on the board, I'm going to jump back to sharing the screen to show you the pages in the book. All right, are we good? I don't want to get ahead of anybody. Anybody still writing? Raise your hand. Shout out on Zoom. I haven't been paying attention. Yeah, okay, so some of these questions you guys ask as well. All right. So this is written out in your book. This is the matrix that I was writing on the board. And so this is the numerator polynomial and the denominator polynomial when you take these determinants. And did you get your answer? I think you were asking, yeah, those straight lines mean determinant of that matrix. And so down below here, they give you NU and D1. And it takes a bit of time. So the denominator, the D1 polynomial, is in terms of these coefficients, A1s to the fourth, B1s to the third, C1s squared, D1s, E1. Then they give you A1, B1, C1, D1, and E1. That's on your handout. And then here's the numerator polynomial. So if you know all of the dimensional derivatives and the flight speed for your airplane, you stick it all into these equations, you crunch away for a while, and you get the numbers that are A1, B1, C1, D1, and AU, BU, CU, DU. You have a polynomial in the numerator and a polynomial in the denominator. And you do the same thing for the second unknown, which is alpha. So here you stuff the right-hand side in the middle column. Isn't this a bizarre rule? Who would have thought? A lot of algebra is like that. You keep the A matrix on these sides and divide by that same determinant. So the determinant stays the same, the numerator changes. And the third unknown is theta of S over delta E of S. And the denominator is the same determinant. Numerator is this polynomial, and you calculate it down here. So in one fell swoop, because we spent the time to put this into a matrix and Laplace it and make it linear so we could Laplace it, now we have solutions in the S domain, and we can quickly analyze the roots of that denominator polynomial and find out the stability like we were talking about last time. We said with any system, we take the denominator polynomial of the transfer function. Those are called the poles, or the roots of the denominator. You look at them, if they have negative real parts, it's stable. One of them has a positive real part, it's unstable. If they have imaginary parts, it's oscillatory, and we're done. We know we can characterize the response. Now, if you really want to calculate an input to output relationship, you can do that. Right, just like any of the systems we talked about last time. If we have, say, the alpha of S transfer function, we got the numerator and the denominator. These are polynomials, and we multiply by delta E of S. So if we wanted to do a step elevator input, we would simply set delta E of S equal to 1 over S, stick that in here, do the partial fraction expansion, which is not going to be easy, right? There's a lot of stuff, a lot of terms, but we got a fourth order polynomial in the denominator and the numerator. So we could do this. You could split it up into the 4 roots and then do the partial fraction expansion, do the inverse Laplace, and then you'd get alpha of t. So you could show what the angle of attack looks like in response to an elevator step input of your airplane. Same thing for any of the other systems, or any of the other unknowns. So it took a while to set all this up. In fact, it's taken most of the semester. But once we're here, we have the tools of Laplace transform and matrices, and we're done. Now we'll do the same thing for the lateral directional forces and moments.
Do you have to calculate back to the roof or not?
You have to calculate what?
Back to the roof?
I don't remember. No, in this homework, all you're doing is going until you get to the matrix, and then you're done. Except problem number 6, I'm going to show you now. It's a different way to write the equations of motion. That's not a big deal. It's just rearranging stuff. In 607, have you guys studied state space form? Yes? Well, then you're good. You know how to do this already. For those of you that have forgotten or haven't seen it, state space form is just a special way of writing differential equations to put them in a standard matrix form. And then you know the solution because it's standard. So I'll show you that real quick. And it's not hard. All you do is rearrange and do algebra. And the one rule you follow is you want all the derivatives on the left-hand side. And on the right-hand side, no derivatives. And not only that, but you can only have one dot. which works because look at our first equation. Let's go back and look at the equations of motion. So we're jumping back before we Laplaced, because this is a different way to do this whole deal. So we're talking about this set of equations here. So look at the first equation. And we got a u dot, and it's on the left side. So that's where we want it. So this equation takes no work whatsoever. So far, so good, right? So that was easy. Okay, so then the next equation is the alpha equation. So we're going to want an alpha dot over here, but no dots on the other side. And I'm not showing that, am I? So let's look at it on the shared screen. We want alpha dot. Let me pop back over here so everybody can see it. I need to write something here so it'll focus. Is that better? Yeah. So we want alpha dot on the left and no dots on the right. This is just the rule. This is standard state space form. So you follow the rules to get it into this form. Okay, so go back to the equations. And these are on your handout, so you can be looking at them. I'll look over here and I go, well, crap, there's an alpha dot here, and there's an alpha dot here. If I can fix that, I just move this alpha dot over to this side, factor out alpha dot, and divide by u1 minus z alpha dot. That fixes it, right? I want an alpha dot all by itself on the left side. Yeah, so what are we going to do about theta dot? Well, we got two different variables in here, but I'm saying I only want one dot and one variable. Should have written that on the left side. So what do we do with theta dot? Yeah, we could say theta dot is q. Gets rid of theta dot. So for this equation, you solve. I'm going to switch back. Believe it or not, I've lost a little weight during COVID, a couple of pounds. I think it's because I keep walking back and forth without my mask and having to go back and get it, if nothing else. So we solve for alpha dot, and we say q is theta dot. Well, that seems like cheating. Q is still there, but there's no dot. So somehow we're going to have to fix that because it seems like we've lost some information. So hang on a second. And then the next equation is going to be the q dot equation. So we got q dot equals, that's our target. Q dot, one variable on the left, one equation for one variable, no dots on the other side. So let's go look at that equation. How are we doing there? We got a theta double dot. But ho, theta double dot is q dot, right? So we're good there. And for theta dot here, we can plug in q. So we're good. How about alpha dot? Well, that's coupled with this equation up here. So to get rid of alpha dot, we take this equation and substitute to get rid of alpha dot down here. Because we're getting rid of all the dots. That's the goal. And so the goal, the standard form is single variable derivatives on the left, no derivatives on the right. And it seems like we've got theta and q mixed in here, don't we? In fact, we've added kind of an unknown. Because in our variables here, in our equations on the right side, so we got q's and we also have thetas. So we've got another unknown that we don't know what to do with. So we need to add an extra equation. Oh, I'm not doing that, am I? Thanks for keeping me on track here. So we're going to substitute in for alpha dot here with the equation above. So with the three equations at the top, we had unknowns were U, alpha, Q, and theta, and that's four unknowns and three equations, but we get an extra equation that tells us how theta dot and Q are related. And that's courtesy of the kinematic equation. So really, we just added the kinematic equation as the fourth equation. Now, if you study this in control system theory, you can take any set of any ordered differential equations, and then you make up names for new variables. And then you just add an equation that says what's the relationship between the new variable and the derivative of the old variable. So like if you have a differential equation that has like x triple dot plus x double dot plus x dot, and you go, how the heck am I going to get that in the form? You say, okay, I'm going to call v x dot. That makes sense. That's velocity. Then I'm going to call acceleration v dot, and you can knock the derivatives down to single derivatives in any differential equation. But we're not doing that. We're doing airplanes, and here it's real natural because of the definitions of how theta and Q are related and things like that. All right, so this is state space form for what we're doing. We have dots on the left and no dots over here. And these multiply our unknown vector here because it's going to be over there. And then you may end up with a vector that has constants in it. And this is state space form. Oh, these will be constants, and this will be times delta E, the inputs. And because this is such a standard form, people call this the A matrix, and they call this the B matrix. And you can go into MATLAB and tell it, my A matrix is that, and my B matrix is that, and it will do everything else for you, because it already has the solutions to this standard form built into MATLAB. And maybe you've done that in 607. Even the Laplace transform stuff's already coded in for different functions. But if you put your set of equations, differential equations, into state space form, then you simply in MATLAB, you say my A matrix is this, my B matrix is this, and you feed it into automated solution techniques, and it will solve whatever you want from the state space form. So problem number 6 is essentially doing what I've told you how to do here. So first equation, you just write down. Second equation, you solve for alpha dot and put Q as theta dot. Get rid of the theta dot. Solve this from Q dot, substitute for alpha dot, and you're good. And then write this equation down, and then you throw them into matrix form, and you're done. The really nice thing about state space form versus the other Laplace method is, if you remember when we did the Laplace in the book, we had to find that denominator polynomial and then look at the roots to find stability, right? We just talked through that. We said, okay, we got to find the A1, B1, C1, D1, find that polynomial, find the roots of the polynomial, and then look at the real and imaginary parts, right? Remember that? To find those roots, once it's in state space form, you simply find the eigenvalues of A, and those give you the roots. And I don't want to do that today, but I'll show you next time. Remind me, I'll show you why. It's not that hard, but I don't want to get, we're probably close to out of time anyway, and I don't want to get things confused. So any set of differential equations, you can always Laplace each equation, put it into a matrix like we did earlier, and solve it that way. It's no problem with that at all. But if you go into state space form, then the solution's already pre-programmed for you. And all you got to do is say, type in the A matrix and say I give A in MATLAB, and it gives you the roots without calculating the A1, B1, C1, D1, and E1. And we'll do that, the final homework in this class, I think it's no, there's two more. You will do this for a particular airplane. You will find the roots using the long method, and you'll find the roots using this, and they'll match. And this is important. Sometimes we haven't taught 607 with state space. A lot of times you'll be interviewing for a job and they'll say, hey, do you know state space form? And you'll say yes, and they'll go, great, because that's what we use. All right, so remind me next time that I'm going to show you that last little bit on the state space form. I have extra handouts, so if you want to take one home to your friends and family, you can do that. Otherwise, they'll get recycled. Where are we? Let's see. That doesn't sound right. It's on the homework. Next Thursday is November 12th, right? So that's when the homework's due. And then your flight test assignment is due on the next Tuesday, and then we're doing the final exam on the 19th. Not the final, the fourth exam. It's on this homework sheet. Pardon?
Busy month.
Yeah. Yes. I haven't started grading it, but it's on my to-do list.